All right, so let's take a look at 7.2. Okay, so as I said, yesterday we had kind of a general introduction to all the rigid motion transformations. Again, those transformations are reflections, rotations, translations. Sometimes you call a translation a slide. Okay, you can do that. Today we're going to focus specifically on reflections. Okay, reflection, it's kind of like flipping. It's like a mirror image. Okay, when we do a reflection, generally you draw a line. Okay, it doesn't have to be horizontal or vertical. It can be on an angle. And you flip it over that line. Okay, however you draw it, you flip it over that line. And when you flip something over a line, the way we're going to do it, that's called a reflection. And the line that you're flipping it over, the thing that's acting like your mirror, that's called the line of reflection. Okay. So we described transformations yesterday as a mapping. Okay, a mapping meaning it starts at a certain point and it gets mapped to a new point. Okay, so what I'm about to do is describe to you in a reflection how are all the points mapped. Okay, and this is going to be for every reflection that you do. Okay, and when I try to think of a transformation, I try to think of it as one point at a time. If you try to think of reflecting an entire picture all at once, that can be confusing to draw. But if you just think about reflecting it one small point at a time, and then like connecting all those points to make a shape, then it's much easier to do the reflection. All right, so that's how we're going to think of it. Okay, a reflection in line M. Okay, so I'm calling line M. That's my line of reflection. It's a transformation that maps every point in the plane to a new point, which we're going to call P prime. That's the reflected point, such that the following has to happen. Okay, there's really a couple different cases. Okay, is the point you're reflecting on the line that you're reflecting or not on the line? Okay. If it's not on the line, okay, this is going to happen. If the point is not on the line of reflection, then if you take your original point and your reflected point, take P and P prime, and if you connected them, the line of reflection is a perpendicular bisector for that segment. Okay, so just kind of a simple example. Let's say this is point P, and then when I reflect it, this is P prime. If I connect P to P prime, since point P was not on the line of reflection, call that line of reflection M. Line M is a perpendicular. It's a perpendicular bisector of the segment P, P prime. Does that idea make sense? The line of reflection is a perpendicular bisector of the segment P, P prime. So what does that basically mean about the distance from P to the line of reflection and P prime to the line of reflection? What's that mean? How about Kira?
They're the same.
Yeah, the same. Exactly. That's a very important characteristic when you do a reflection. The original point measuring the distance to the line of reflection, and then the reflected point measuring the distance to the line of reflection is always the same. That distance won't change.
Hager.
Yeah.
What if you have like a shape that's on the line you're reflecting on?
Yep, we're going to talk about that right now. So what happens, we'll get to a shape, but we'll start with a single point. Okay. What happens if you had a point that was right on the line and you wanted to reflect it? What do you think happens to that point? It just stays there. If a point is on the line of reflection, The original point and the reflected point are the same point. It just stays there. Okay, so those are basically your two cases. Okay, here's another sketch. Okay, in the sketch on the left, P is not on the line of reflection. When we reflect it to P prime, those two segments are equal in length. And that's a perpendicular bisector of P prime. Now here's the case where P is on the line of reflection. If a point is on the line of reflection, what's the distance of that point to the line of reflection? 0. So when you reflect it, the distance stays 0, which means it's right on the line. Okay. Any questions on those two cases? All right, so let's take a look at something else first. Okay, so I'm going to show you an example of an image. Okay, and I just want you to look at it. Whoa! Just try to look at it for a second.
Are you going to ask us what we see in that picture?
Yeah, what do you see in that picture?
I see clouds.
See some clouds? Well, good. It's supposed to look like clouds, so that's good.
I see a goat. I see a dragon.
How about in terms of like transformations? Do you notice?
I can't see that.
I see a man
It's a reflection.
in a hallway.
Can you explain what you mean by reflection, Denver?
It's on the whole side.
Okay, which way is it reflected? Over the x or over the y-axis?
Both.
Yeah, it's actually reflected over both. So by doing that, if you took another section of, we'll call this sky, okay? If you took another section of sky and put it next to it, on the edges, everything would line up nicely, and it would make a pattern. So this edge on the right would match up with that edge on the left. Okay? This part on the bottom would match up very nicely with that part on the bottom. Okay? So you get kind of a pattern. Okay? And the reason you might want to do something like that is because let's say you're trying to make a game. Okay? You had a game and you wanted to have sky in the game. Well, sky is something that's infinitely big. So if you wanted to create an image that was infinitely big, it's going to be a very large picture. Okay? So what you can do instead is use a pattern that repeats. It's the same pattern repeated over and over, but it kind of tricks someone into thinking it's infinitely big when it really isn't. It's just a pattern repeating over and over. Okay, so I'm going to show you that right now.
Isn't that the same thing when you're using wallpaper to, when you're putting wallpaper up on the wall, that's what you try to do?
You line up the pattern, yep. All right, so this program I'm about to show you, this is something that I did when I was in grad school. It wasn't really for studying reflections and transformations. It was more basically I gave a user an environment, and they had to navigate through it without hitting objects in it. Okay, and I gave them a few different ways to do it. One of them was a joystick. Okay, they could use that. One of them was a keyboard, and I even had this other fancy device. It kind of had like a trackball on it with some keys and levers, so they could try that too. All right, so the purpose was to see how quickly they could get through my little maze. But I just want to show you a picture of the sky. Okay, and actually, let me.
Can I play your game, Mr. Hager?
Yeah, maybe after we can do that.
Sweet.
Okay. So as you're moving around, you get this illusion that the sky is really infinitely large. Okay, when it's not. Okay, you could definitely see there's a pattern to it, but it's also a lot better than trying to create something that is infinitely large picture. Okay, because computers only have so much memory, so you can't have something infinitely large. So you try to make a pattern, okay, like that. And you can, let's see, we can look up at the sky. We can look back down.
What's the story of your video game, Mr. Hager?
We can go.
Whoa, you can fly?
We can fly. Now we're getting up above the sky. Now we're looking down. All right, so the idea there, I just wanted to just see an example where you can take an image, do some reflections with it to create a pattern that looks realistic. And if you look at the size of that picture, it's only 193 kilobytes. It's very, very, very small. Okay? Versus if I wanted to create an image that was really unique, could be a lot larger. Okay? So there's an example where you can use reflections. And there's a lot more sophisticated ways to do it than I did it. But that's a very simple way to make something that looks somewhat realistic. Use reflections.
How come your picture is bigger than the game? If the picture is 193 kilobytes and the game is only 1 kilobyte, so it says.
Yeah, remember though, when you're coding a game, code is just text. Text takes up almost no space at all. Images are huge. Images take up a lot of space. Yeah. So this, in fact, I'll show you really, really quick if I have it. So this is the code that runs the game, but it's all text. It's just text. It's a lot of text. Okay, but it does different things. Okay, so there's text that displays, like if a user hits the wall, this text tells me which wall they hit. Did they hit the left wall, the right wall? Did they hit the top of the tunnel? Okay, all kinds of stuff. But when you write code for games, this is somewhat how it can work. This is C++ code. But yeah. See how much smaller it is? All that text, if you printed that out, that's probably like 20 pages of text. It's only 59 kilobytes. That one picture I showed you was bigger than that. Pictures take up a lot of space. So that's why. All right, so now let's look at some more with reflections. All right, so let's try graphing these two reflections. Okay, first one they want us to graph is the point 2, 2. Okay, they want us to graph that in the x-axis. So when they say graph it in the x-axis, it means reflect it over the x-axis. Yeah, that's what that means. Okay, so this is x, this is y. Anybody think they can tell me the coordinate where 2, 2 is going to go if you reflect it over the x-axis? Yeah?
2, -2.
Yeah, it's going to go 2, -2. And that might be a hint at how you do this in general. Okay? If you have an x and a y value, maybe one of them stays the same, and you just make the other one negative, if you want to reflect in the x-axis. We could maybe come up with a pattern for the y-axis too. Okay, so we'll look at that after. Okay, so there's h prime. How about g? We're going to reflect it over the line y equals 4. What kind of line is that? Y equals 4. We got to sketch that. How do you sketch the line y equals 4? Yep.
We're rotating it, well, reflecting it over 4.
Yeah, can you just tell me how to sketch that first? Y equals 4. And then we'll do that reflection.
Point on 0, 4. No, 4, 0. And then draw a vertical up.
Okay, y equals 4 is not going to be a vertical line.
It's going to be horizontal.
It's going to be a horizontal line. Yeah.
Go up 4 on the y-axis with the x line.
So up 4 and then
And then you just go across the here.
draw a line. So that's the line y equals 4. Okay. Y equals a number horizontal, x equals a number vertical. Okay. Now you're reflecting the point G over that line. What's going to happen when you reflect that? Right, it's right on the line of reflection. So that is G prime. It doesn't move. Okay, any question on that? Two reflections. Okay. So let's see if we can come up with a pattern. Okay, when we reflect over x and y. So if you reflect a point over the x-axis, what value do you think stays the same in the coordinate? If you reflect something over the x-axis, what part of that coordinate will stay the same? Selena? Yeah, the first number, the x value. If you reflect over the x, you put the point down here. The x value stays the same. How about the y value? What happens to that? Very simply, it just becomes
Go negative,
it becomes negative. What if it was negative and you reflected it?
then it goes positive.
We go positive. So the point is, if you have a coordinate, x, y, and you reflect over the x-axis, it becomes x negative y. Okay, what if you reflect the other way? If you had a point and you want to reflect it over the y-axis. So then this point would end up over there. Anyone have a guess what the pattern would be for that? Oh, James?
Which question?
So if we reflect a point over the y-axis, what do you think the formula is to do that? Shortcut, kind of like we did up here. Yeah, it's going to be negative x, y. When you reflect over the y-axis, the y value doesn't change. You're not changing the height. You're just changing where it was in terms of x. Now it's negative x. Okay. So for example, if you reflected 4, 2 over the x-axis, we go right there. 4, negative 2. So notice the y value became negative. If you were to reflect this over the y-axis, we go right there. It would be negative 4, 2. The x value became negative. Okay, any question on that? So that's a shortcut for flipping over the x or the y. Now, if you just had another line at an angle, okay, let's say you had a line with a slope of something and a y-intercept of something. That could be a little bit more complicated to figure out a formula. You could do it, okay? But it might be a little bit more harder, but it's also a little bit more realistic. Okay? Generally, reflections aren't always over a line that's perfectly vertical or perfectly horizontal. A lot of lines you reflect over can be at angles. Okay? Especially in a video game, like if you were looking at a mirror but you weren't right in front of it, you were looking at it at an angle. Right? Or you were looking into like a puddle on the ground that was reflecting. Okay? So there's different kinds of reflections that can happen at different angles.
What of a shadow?
Shadow? A shadow, that's a whole nother aspect of game design, yeah. So a lot of shadows and reflections are drawn with what's called ray tracing. So you imagine a ray of light and how it would travel and kind of like bounce off things. That's a little more complicated to do, but you can do it. And then you can also give your objects in games different reflection rates. For example, like this textbook. It's a little bit reflective. You know, the front shines a little bit, but it's not really highly reflective. Okay, not like a mirror. So when you make a game, you can give different objects in the game different reflective properties. Let's say you had a chrome sphere. That'd almost be like a mirror. You could see, if you put that in the middle of a room, the whole room should almost be reflected in that sphere. That gets a little complicated, but it's pretty neat. But yeah, and you can do shadows that way too, with lighting. Sometimes you have like a spotlight. Okay, so like if you're on a stage and a light hits you, okay, the cutoff for that light is very sharp, meaning, you know, you might be in the spotlight here, but then you step 3 feet to the left and now you're out of the spotlight. Versus a light bulb in your house, it's just kind of a general light. Lights the whole area. It's not like if you step to the left a little bit, you're not in the light anymore. You know what I mean? Yeah, it's like a beam versus just being spread out. And that creates different shadows too. So there's all kinds of stuff with shadows and light. All right, so here's a theorem about reflections. Okay, reflections are an isometry. Okay, what does that mean? If something is an isometry. We talked about that yesterday. Okay, so the shape, anybody explain, what does that mean? The shape stays the same, but it's in a different spot. Okay, yeah, an isometry is a transformation that preserves length. Okay, so the length of the sides won't change. Okay, Luke, what else?
It can be like translated or like reflected, but it always has the same angles and stuff.
Yes, so there's all kinds of things that are preserved in an isometry. Angles are preserved, lengths are preserved, parallel lines stay parallel. The area that it was before, it's the same area after. Okay? All right, so to prove the reflection theorem, we're not going to go through the proof, but I'm going to show you the 4 cases you would have to go through. All right, so suppose that we're thinking, we'll make it very simple. You're just reflecting a segment. Okay, you're reflecting a single segment, segment PQ. Well, the 4 cases that could happen is P and Q could both be on the same side of the line that you're reflecting. Right, so you could have, this could be P, and this could be Q, and you're reflecting it. Okay, P and Q could be on opposite sides. P could be on one side of the line of reflection, Q could be on the other. Okay, you could also have one point that's on the line of reflection, and PQ is not perpendicular to M. And then you could have a point that is on the line of reflection, and PQ is perpendicular to line M. Okay, all those cases are drawn out. I'm not going to sketch each one, but they're all on the bottom or top of page 405. Okay, I think I'll sketch the last 2 because those can be a little confusing. It's kind of like, not sure what's happening there. So let's sketch that 3rd one. Okay, you've got a line of reflection, and it says one point is on the line of reflection. We'll call that P. But PQ is not perpendicular to the line of reflection. Okay, so let's put Q right there. Does everyone agree that the red and the black line are not perpendicular?
Yes.
Okay, that's case 3. Case 4 says, all right, we have a point on the line of reflection, like Q, but PQ is perpendicular to the line of reflection. Okay, so that would be like that. That's case 4. So when you reflect this one, basically it just ends up looking like that. Basically it just flips it right over the line. It almost looks like it's just continuing. Okay, when you reflect this one in red, it's a little different. It would look more like this. Okay, so that's the 3rd and the 4th case. Okay, if you want to see pictures of the other 2 cases, you could just look at the top of page 405. We're not going to go through all the proofs of each one of these cases. Okay, any questions on that? Kind of 4 different things that can happen. All right, so next thing we're going to look at is what's called a line of symmetry. Okay, so we say that a figure has a line of symmetry if the figure can be mapped onto itself by a reflection over a line. Okay, so here's an example. The letter A. If you draw a capital A like that, it has a line of symmetry. Because I could just take the left half of that image right there, reflect it, get the right half, and it lands right on top of it. Does everyone see that? How if you reflected the left half, it would land right on top of the right half? That's a line of symmetry. Okay, how about a capital B?
No.
They have a, that's X.
I mean, if you drew it something like this.
Transverse.
Yeah.
Yeah. So a capital B would have a line of symmetry. If you took, this time it's not vertical, it's horizontal. If you took the top half and reflected it, it would land right on top of the bottom half. There's a line of symmetry.
No.
Okay, yeah, we'll talk about O in a second. Anybody think of a letter that would have, the capital letters I think are easier. 2 lines of symmetry?
X.
X. Let's think about it. If you flip the top half down, it lands on the bottom. If you flip the left half over, it lands on the right.
I think there's more though.
But there might be even more, yeah.
Diagonals.
Because imagine you drew in a line of symmetry like that. Now, this segment wouldn't move, right? It's right on the line of reflection. But this segment would be reflected down there. So there's a third one, and then a fourth one. So I think an X might have at least 4 lines of symmetry.
Or a perfect circle O.
A C? No.
All right, so a C does have a single line of symmetry.
Well,
How about an O?
how can we find out how many lines of symmetry there are?
Well, somebody has infinite amounts.
How can you find out how many lines of symmetry there are?
Yeah.
There's no formula for doing it. It's more of a visual process. You
So you
really,
would have to do it.
yeah, you have to look at I'll give you an image. You have to look at it and figure it out. Okay, how about an O?
There's no equation to find that one?
Yeah, there's an infinite amount. You can draw a line of symmetry. There's only one condition. The line of symmetry has to do what? It has to go through the center, yeah. It has to go right through the middle. If you draw any line that goes through the middle, it's a line of symmetry. Okay, so there's infinite lines of symmetry there. Capital H. Okay, capital H, I think you could only get away with 2. You couldn't draw something on the diagonal. I'm not sure that wouldn't really work. All right, so capital H, you got 2 lines of symmetry. Okay.
C?
Or like a capital Z. Let's look at it.
No.
Yeah, I don't think there's any symmetry there, because if you if you reflected it, this point would end up down here, so that wouldn't work. If you did it this way, yeah, this would end up over here. So yeah, I don't think a Z has any lines of symmetry.
Pause.
Okay, another way you can figure out if something has a line of symmetry, okay, you could take, if you had a mirror, draw half of the letter, right? Then take your mirror and put it right on the edge of your picture. If you look and you see the whole image and it looks correct, then that's a line of symmetry. Okay? If you hold up the mirror there and you look at what you drew and you look at what's in the mirror and together it doesn't look like the letter you thought, then that's not a line of symmetry. Okay, so let's talk just about one specific shape, a hexagon. So if somebody asks you, how many lines of symmetry does a hexagon have? Well, it depends on how you draw the hexagon, or pentagon, or any shape. Okay? So hexagon, we'll look at this one, can have different lines of symmetry depending on the shape. Okay, that's a hexagon. Okay, 6 sides. How many lines of symmetry there? Okay, we definitely have one. Somebody describe where it is. Yeah, it's like the y-axis. Okay, if you flip the left half, it would land right on the right. Anything else? No.
Bottom was a little more pointy.
Yeah, the top and the bottom shape aren't quite identical. Okay, as Denver said, the top one is a little bit more pointy. The bottom one is a little bit more shallow. So there's only one line here. One line of symmetry.
If it was regular, it's really hard.
Okay, so yeah, let's look at a different one.
1, 2, 3.
Okay, somebody describe where's one line of symmetry there?
Y.
Okay, the y-axis going right through the two vertices there. If you flip just like that, that'll work. Where else?
X.
Okay, where? Where would you put it?
In the center of the
Yeah, right,
segment.
right in the center. Okay, so that's a line of symmetry.
Then all the rest of the 4 sides, well, 2 sides.
So you think if I drew a line right through the center of these two sides, that would be a line of symmetry? So if we take out the other ones, just so we can see it a little clearer. If you get confused, focus on one point. Look at that point. Draw a line perpendicular. And then imagine taking this, cloning it. That's where this point would go if you reflected it over that line. Wouldn't land on the figure. So that's not a line of symmetry. Yeah, but that's still a good guess. Yeah, there are no more. Okay, in this shape, there's only 2 lines of symmetry. Okay, any question on that? There's only 2. Okay, how about this one? Any thought? Just throw one line out so we can draw it.
That'd be 12 though, right?
Okay, tell me where 1 would be.
That'd be 1 on each vertex.
It has to be divided by 2.
What do you mean by each vertex?
So every point where the lines connect, and there would be 1.
So like this? That goes through each vertex?
That's the center, you know what I mean?
Oh, through the center.
Opposite center, opposite vertex.
Yeah, kind of the vertex that's opposite. So that's a line of symmetry.
And then you got the ones on the sides too, like right directly in the middle of the sides. You got one of those, so you can multiply 6 by 2. Because it's got 6 sides and 6 vertices.
Yeah, but each vertex, it takes 2 vertices to make one line.
Right, so there's 6 lines of symmetry.
So you can put, so that covers
Then just 6.
4 of the vertices.
That'd be just 6 lines.
That covers all 6 vertices. Okay, so as Luke just said, you get a line of symmetry through those opposite vertices.
This board, though,
And then where else do you get them?
on the faces.
Thanks for answering my question, Connor.
Well, careful. Faces, usually that's something for a 3D shape.
Yeah, see, you got it wrong.
So we got,
On each side.
To the
Each side of each
sides.
side.
So Spider-Man,
You just
Yeah.
told me, Connor?
it's a face.
okay, so you're going to get,
Whatever the opposites around me.
so you're going to get a line of symmetry. Okay, you get a line of symmetry vertically through those 2 sides. Okay, you're going to get one through that side, and you're going to get one through those 2 sides. No, there's not infinite. That's it.
Oh.
Anywhere else you draw a line of symmetry, it won't work. Okay, there's only 6. What's the only shape we studied so far that had infinitely many lines of symmetry?
Circle.
Yeah, a circle. Okay, so six lines of symmetry. Any question on that one? Okay. All right, so our last, let's finish up with this one. Okay, it says solve for x and z. Okay, what kind of transformation have I done here? That's a reflection. And anybody remember when you reflect, do lengths change? No, it's an isometry. So can somebody give me an equation to find x? You got to use part of what's up above, part of what's below.
Your x equals 4.
Right. Okay. If this vertical line on the bottom is 4, and this vertical line on the top is 4, it's just a reflection. Okay. So how would I solve for x?
Divide by 3.
Divide each side by 3. We get 4/3. Okay. How about somebody else? What would be an equation to solve for z? Yeah. Right. The side that's 2z minus 1 and the side that's 5 are reflections of each other. So they're exactly the same length. So 2z equals 6. And how much is z? Yeah, z is 3. Now if they said, you know, you could find if this was like a right angle, we could use Pythagorean theorem to find another side in that triangle if we wanted, but that's all they want. Okay, any question on that? All right, so that's reflections.
Sorry, I've been curious on class, what is that?
All right. So the homework, it's on 407. 15 to 21, just odds. 22 to 29, I want you to do all, but you can skip number 24. You don't have to do 24. And then at the end, it kind of jumps around. So 31, 32, and 37, 38, and 41, 48, and 49. Okay, and for MCAS, do the open response. Okay, so we'll go over that tomorrow, and then we'll have our test on 6.4 to 7.2.